Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to extend our knowledge of the policy gradient method by looking at continuous action spaces. Remember that both of the environments we've looked at so far, cartpole and mountain car, both have discrete action spaces. Luckily, there is an environment called mountain car continuous that gives us continuous action spaces, so we have something to test this out on. So if you think about our current policy model that allows us to choose from a discrete action space, what's the main idea? The main idea is that the output of the model is a probability distribution that we can then sample an action from. So if we want to have a continuous action space to sample from, how might we go about creating a distribution for that? What distribution might be appropriate? Well, technically, you could choose any continuous distribution, but the Gaussian seems like a good place to start. Remember that a Gaussian has two parameters, the mean and the variance. So in order to create a parameterized policy, we would parameterize the mean and variance. Let's assume for the purposes of this lecture that both the mean and variance are linear in their parameters. So in other words, mu is equal to theta mu dotted with the feature vector, and the variance is equal to the exponential of theta v dotted with the feature vector. Alternatively, we could use the soft plus function instead of the exponential. So why would we want to use the exponential or soft plus after multiplying the feature vector by theta v? Well, remember that the variance must be positive. But using gradient descent, theta is unbounded. Therefore, in order to make sure the variance is always positive, we can exponentiate the output of the dot product or use the soft plus. Recall that the soft plus is asymptotically the same as the rel u, but it can't actually go down to 0, which is useful. This might be a little better than the exponential, since the exponential grows very fast if its input is large. Once we've defined the model, we have to figure out how to update it. Luckily, the principles of the policy gradient method don't change just because we've redefined the policy. We still have the same cost and updates as before, and of course we can replace plain gradient descent with any of its modifications, like eta grad or RMS prop. This is an important idea, so it's worth saying again. The policy gradient method doesn't change just because you redefine the policy. The policy can be any function you make it, and the policy gradient method still applies. So you can have any kind of output distribution, any kind of parameterization, the method remains the same. One last thing to think about. This wouldn't be possible if we didn't have policy gradient methods. Consider regular Q-learning with function approximation. Function approximation of the action value q lets us handle infinite state spaces, but not infinite action spaces. Remember our earlier strategy. We created a different linear model for each action, and then took the argmax in order to determine what action to do at any step. Deep Q-learning is the same, where you have a neural network for multiple output nodes, one for each separate action. Because we need a separate output or model for each action, this clearly can't scale to an infinite number of actions. So with Q-learning, a continuous action space is impossible, but with policy gradient methods, it is.